All right, we can start. Welcome, everyone. It's a great pleasure to see you all here. Those of you who visited us before, as well as new faces. Last we held this meeting in person was in Abu Dhabi. It was at the end of January, 2020, and then of course COVID hit, right? And after that, the last two versions of this were nicely held by the Singapore group. Fei and Meng Xuan, and it had to be online, although that went nicely. They saved the series, we appreciate that. And now it's great to bring back this to being in person, right? And it's so lovely to see you all in 3D, right? But although last minute matters prevented 3 colleagues from being here, Mike Duff, Eric Sharp, and Meng Xuan Tan. But Eric and Meng will join us via Zoom. So we're going to have 2 Zoom talks. Since that last meeting, we launched the new Center for Quantum and Topological Systems under the umbrella of the NYU AD Institute and supported by our partners, Tim Keen. And we thank them so much for their continuous support. So CQTS is sponsoring this workshop and hopefully future versions of this. In terms of activities, we have a weekly seminar, Geometry, Topology, and Physics, and a weekly colloquium, the Quantum Colloquium, and we're going to have another workshop and a conference coming up this year. So in March, we will have a workshop on TQFT and cobordisms, and then in May, we're going to have a conference on quantum information, quantum matter, and quantum gravity. We are happy that we have a very exciting program in this workshop, and we're going to have several themes, and they're going to showcase the reach of M theory that, as we all know, subsumes string theory and quantum field theory as well as connections to mathematics. Especially geometry and topology. So in today's opening session, we will see that showcased in the talk of Ashoke Sen on string theory, and then on the talk of Neil Lambert on M theory, and on the talk of Dimitrios Tsimpis on supergravity. So Ashok also gave a talk in the other conference, a companion meeting, and we're very grateful that he stayed for this meeting as well. So we look forward to a great conference, and we look forward to all the interesting talks, and welcome you all. And now we can start with Ashok's talk. Okay. So it's a pleasure to have Ashoke Sen from ICTS India, who's going to tell us about D-instanton amplitudes in string theory. Yes, it's up to you.
Use this one, it's okay. Okay, so first of all, I'll thank the organizers for inviting me here. In fact, the last conference here was my last before the pandemic, and this is almost the first after the pandemic. Okay, so it's a good opportunity. So what I'm going to talk about today are D-instanton amplitudes in string theory, and please feel free to ask questions in the middle, because I think there will be plenty of time. And so what I'll describe is some work that I have done more or less in the period between the last conference here and this one. Okay. Here are my various collaborators on this subject over several years. And I should also mention that there are parallel developments. In fact, the whole subject, the study of D-instantons in string theory in recent years started with the work of Harvard group. So what I'll plan to do is to first introduce the notion of D-instantons, what they are and what their role is in string theory. Okay, and then we will see what are the difficulties in carrying out amplitudes induced by D-instantons and how we resolve. So D-instantons. So the simplest description of D-instantons is that they are just like ordinary D-branes, which are given by putting appropriate boundary condition on open strings, whose ends can move on the D-brane. But what distinguishes them from ordinary D-branes is that they do not extend in any of the non-compact directions, and that includes the time direction. So these are typically constructed in the Euclidean theory, and they are localized in all non-compact directions. And because they are localized in all non-compact directions, they have finite action. And because these are D-branes, their action has the structure that it's some constant over the string coupling GS. And you can regard them as some kind of classical solutions. Thank you. We can regard them as some kind of classical solutions in string theory. Okay. So the role that they play is to give non-perturbative corrections to string amplitudes. Okay, and these are proportional to e to the minus c over gs, because the action of the D-instantons is c over gs. Okay. So these are analogous to instantons in quantum field theory. Okay, except that in quantum field theory you will get a square of the coupling constant here. Okay. Whereas because these are D-branes, you get 1 over the coupling constant in the exponent. But the full amplitude induced by D-instantons, of course, is not just e to the minus c over gs. So for any given process, okay, the structure of the D-instanton amplitude is that you have this overall factor of e to the minus c over gs. Okay, but then there is a perturbation expansion in gs. Okay, it goes the whole series expansion in gs. Okay, and that perturbation expansion, okay, how to the calculation of the coefficients of those powers of gs, okay, is done by the worldsheet theory of closed and open strings. Okay, so these provide the formal expressions for the D-instanton contributions to this amplitude. Okay, and I have said this word formal, and we will see in what sense this expansion is a formal expansion. Okay, and the main goal of this talk is to describe how we can make this formal expansion into something that is calculable. Okay, so these are given. So this worldsheet theory, the actual coefficients of e to the minus c over gs, okay, they are given as integrals over the moduli spaces of Riemann surfaces with boundaries. Okay, and the boundaries basically end on the D-instanton. Okay, so that's the structure, and we'll see some specific worldsheets, the examples of worldsheets that appear in the D-instanton amplitude as we go along. Okay. Now, before we describe how to calculate D-instanton amplitudes, okay, let me address some of the questions that come naturally to mind. Okay, and first question is the following. Well, I mean, this is a question that I'll try to address, but there are various answers. That given that string perturbation expansion is an asymptotic series, okay, does it make sense to compute non-perturbative contribution? Okay, because you don't know typically how to resum the string perturbation expansion. Okay, so if we don't know how to resum the string perturbation expansion, is it meaningful to talk about corrections of order e to the minus c over gs? And here I'll provide two answers to this question. Okay, the first answer is more practical. Okay, namely that in many cases one finds that the perturbative contribution to some specific quantities either vanishes or terminates after a finite order. Okay, so the perturbative contribution is completely well defined. Okay, there is no resummation that is needed. Okay, and in this case, of course, it is meaningful to talk about non-perturbative corrections because the perturbative corrections are fully understood. And here are some examples. Okay, the first is a series of examples. These are terms protected by supersymmetry, okay, which either do not receive any perturbative correction or the perturbative correction terminates. Okay, and there are various examples I have given here. For example, in type 2b string theory in 10 dimensions, the Riemann to the 4th term, there is one term in the effective action, its coefficient, one can show the perturbation expansion of this coefficient terminates at finite order. Okay, so it is meaningful to ask what are the non-perturbative corrections to these coefficients. Okay. The second example is a modularized space metric in n equal to 2 supersymmetric theories in D equal to 4, which basically means type 2A or type 2B string theory, compactified on Calabi-Yau manifolds. Okay. Or superpotential in n equal to 1 supersymmetric compactification in D equal to 4. Okay. These are various examples where the perturbative contribution either terminates or doesn't exist at all. These are more examples in lower dimensional string theory. Okay. So this two-dimensional bosonic string theory, which is also sometimes referred to as C equal to 1 string theory. Okay. Here, the theory is known to be non-unitary. Okay. There is a specific source of unitarity violation in this theory. Okay. But that violation of unitarity occurs at a non-perturbative level. Okay. Perturbation theory is completely unitary. Okay. And it's the D-instantons that are responsible for unitarity violation. Okay. So there again one can use D-instantons to compute unitarity violating amplitudes, and it's completely well defined. Okay. It doesn't mix with the perturbation expansion. Okay. There is a close cousin to this which is known as the two-dimensional type 0B string theory. Okay. This theory is unitary. Okay. But again here there is a class of S matrix elements, okay, which is called the barrier penetration. Okay. These are the particular class of S matrix elements that require barrier penetration. Okay. These again occur only via D-instanton effects. Okay. And so the perturbation expansion vanishes for these, and the D-instanton effects are the leading contributions. Okay. So clearly it's meaningful to talk about D-instanton contributions. But there is another answer to this which is more abstract, okay, and that is the following. Okay. That the D-instantons, okay, describe non-trivial saddle points of string theory. Okay. So the trivial saddle point is a perturbative saddle point. So the perturbation expansion in string theory you can think of as a result of carrying out some path integral in the saddle point approximation, okay, and the saddle point being the trivial Gaussian fixed point, okay, that the perturbative saddle point. Okay. So these are non-trivial classical solutions, so they are non-trivial saddle points. Okay. And the worldsheet theory of open and closed strings basically gives a systematic perturbation expansion of the path integral along the steepest descent contour of this saddle point. Okay. So this is a quantity that is well defined by itself. Okay. The fact that there is another saddle point which is perturbative and which may be dominant, okay, doesn't affect this description of what you are computing. Okay. So D-instanton amplitudes basically compute the systematic perturbation expansion of this particular contour integration. Okay. So this, as I said, is an interesting quantity by itself, but it has also more practical use. Okay. For example, in many dualities, okay, we may have a situation where on neither side we know the full non-perturbative description of the path integral. Okay. Namely, we don't know the full contour over which we should integrate to get the non-perturbative description of the theory. Okay. Nevertheless, okay, in these two dual descriptions, we can compute the contribution from each saddle point independently and compare. Okay. And these are provided by the C less than 1 string theories, okay, where on the one side you have a set of string theory, okay, regular string theory, and on the other side you have matrix models. Okay. The matrix model has certain saddle points, and you can calculate systematically the perturbation expansion around those saddle points, calculate the steepest descent contour, the steepest descent integral through those saddle points. Okay. And you can compare them with specific D-instanton contribution on the string theory side. Okay. So again, this is a meaningful comparison that one can do, and this is irrespective of the fact that many of these saddle points are non-perturbatively suppressed compared to the perturbative answer. And this could shed light on resurgence in string theory, okay, where resurgence is the phenomena that the perturbative and the non-perturbative contributions seem to be related. So what we will do in this talk is to focus on describing how to compute D-instanton amplitudes, and we will focus on single D-instanton amplitudes, just for simplicity. Okay. In principle, this is extendable also to multiple D-instantons. Okay. So now let me describe the systematics of D-instanton induced amplitudes. Okay. What does it involve to compute an amplitude induced by D-instantons? So the first thing that is different for D-instanton amplitudes compared to the conventional worldsheet amplitudes that we are familiar with, okay, is that individual world sheets with boundaries on the D-instanton do not conserve energy or momentum. Okay? And that happens because D-instantons are localized in space and time, so they break translation invariance. Okay? The D-instanton boundary condition is not invariant under translation either along space and time or time direction. Okay? So they do not have energy momentum conservation. Okay? And as a result, the disconnected world sheet gives the same kind of contribution as connected world sheet. Okay? They contribute even for generic values of external energy and momentum. Okay? So let me make this a little more clearer. So in normal quantum field theory, right, we can write Feynman diagrams, and we normally ignore the disconnected Feynman diagrams because they have separate delta functions associated with each connected component. Okay? So if you take momentum to be generic, consistent with overall energy momentum conservation, okay, then the disconnected diagrams don't contribute because they impose additional constraints on the energy and momentum. Okay. The same is true in string theory. The normal perturbative string theory, you don't include disconnected diagrams because at a generic values of energy and momentum, those diagrams don't contribute. Okay. But for D-instantons, because we do not have energy and momentum conservation on individual world sheets, okay, we have to include the disconnected contribution. Okay. Later on, we will see how the energy momentum conservation is restored. Okay. Of course, the full amplitude should have energy and momentum conservation, but we will see how it is restored at the end. So now, with this understanding, let's try to understand what will give the leading contribution to D-instanton amplitudes. So we know that in string theory, the perturbation expansion, okay, has GS raised to the power minus the Euler character. Okay. So in some sense, you have to maximize the Euler character of the Riemann surface that is involved. Now, how do you maximize the Euler character? Okay. Imagine that you have a given set of external closed strings, okay, which are denoted by these crosses, the vertex operators. Okay. Each disk has Euler number 1. So the more disks we can have, the higher is the contribution, right? Because each disk gives a factor of 1 over GS. So you need to maximize the number of disks, okay, to get the leading contribution. And the second point is that annulus, okay, has Euler number 0. So it doesn't matter, you can use as many annulus as you want. Okay. It will not give any suppression in powers of GS. Okay. So you cannot say that we consider amplitudes with only no annulus or 1 annulus or 2 annulus, they are all of the same order. Okay. So you have to resum the annulus contribution, and that is captured as an exponential. You can show that the combinatorics works out correctly. So you have an exponential of the annulus contribution. Okay. So this then is the leading contribution. This is the structure of the leading contribution to a D-instanton amplitude of a set of external closed strings. Okay. So here you have exponential minus C by GS. This is the D-instanton action. Okay. Then you have the exponential of the annulus, okay, because you can use as many annulus as you want. Okay. And then you have product of disks with one closed string on each disk. This is the leading contribution because this maximizes the number of disks. So when you go to the next order, okay, we will of course have more possibilities. Because suppose you want to go to one higher order than GS. Right? What can you do? We can give up one disk. Right? So you lose the power of 1 over GS. Okay. So giving up one disk means that instead of inserting one closed string vertex operator on a disk, you can sometimes, one of the disks, you can insert 2 closed string vertex operators. Okay? So then you lose a disk, right? Because you have one less disk compared to what you had before. So that's this kind of diagram. Or we can replace a disk by an annulus. Okay? This gives 1 over GS. If you replace it by annulus, you get order 1. Okay? So that's this kind of contribution. Both are suppressed by order GS compared to the leading contribution. Okay, so these are the examples of the kind of graphs that you will get at the first subleading order, and then you can continue this. Okay, the same philosophy, right? You have to check how many parts of 1 over GS you are getting to determine at which order it contributes. So this way we can write down the expression for the D-instanton induced amplitude to any order in string coupling. And then as you do in the standard string perturbation theory, you have to integrate over the moduli space of these Riemann surfaces with boundaries. Okay, that gives, in principle, the coefficient of e to the minus c over gs, okay, to a given order in gs. However, this is a formal expansion, okay, but this has problem, and that will be the main topic of this talk. These moduli space integrals actually diverge, okay, and they diverge from regions of the moduli space where the Riemann surface degenerates. And in order to make sense of these degenerations, of these divergences, and extract a finite result, we need the help of string field theory, okay, and this is what I will try to explain in the next 2 slides. So degenerate Riemann surfaces can come from various sources. For example, in this diagram, right, when one of the vortex operators come close to the boundary, that's an example of a degenerate Riemann surface. In this diagram, right, when one vortex operator comes close to the boundary, or when the length of this circumference becomes large compared to the width, right, that's degenerate Riemann surface. So let me now explain, okay, why string field theory is useful for dealing with these divergences, right? So this will also explain where the divergences are coming from, right? What kind of divergences we encounter when we do integration over the moduli space of Riemann surfaces. So first let me say what string field theory is. So in one sentence, string field theory is a regular quantum field theory with infinite number of fields, one for each mode of the string. And the perturbative amplitudes in string field theory, as in ordinary quantum field theory, are given by sum of Feynman diagrams. And in this Feynman diagram calculation, the propagator of the theory is just 1 over L0, where L0 is the worldsheet scaling generator, okay, which is called the Virasoro generator, 0 mode of the Virasoro generator. Now we can make connection between this and the usual propagator that are familiar with in quantum field theory by noting that the L0 eigenvalues are in fact precisely of the form k square plus m square, where k is the momentum that the string carries and m is the mass of the string mode. Okay. So it's not that different from what we normally call propagator in a quantum field theory. Okay, it's just that here you have an infinite set of fields, and all those, okay, propagators are captured by the single L0 inverse. Okay. Of course, it actually contains infinite number of fields because L0 is a big matrix, infinite dimensional matrix. Now the other feature of string field theory, okay, and that's why it is a string field theory, is that it is designed, all its interaction terms are designed so that formally the sum of Feynman diagrams reproduce the worldsheet expression. Now here comes the main point of this analysis, that when you say that sum of Feynman diagrams reproduce the worldsheet expression, okay, we have to give a little more detail of how it reproduces the worldsheet expression, right? What do you mean by saying that it reproduces the worldsheet expression? Because in the worldsheet language, we saw that you have integration over the moduli space of Riemann surfaces. When you sum over Feynman diagram, of course, there is no such integral, right? You integrate over momentum, but there is no integration over moduli space of Riemann surfaces. Okay. So the natural question would be, what is the connection between these two expressions, right? The Feynman diagrams of string field theory and integration over Riemann surface moduli in the worldsheet description. Okay. And here is the simple way we make this connection, okay, that we note that we can write L0 inverse formally as an integral of this form. Okay, this is 1 over L0. T is what is normally called the Schwinger parameter in quantum field theory. Okay. So the idea is that you write down a string field theory Feynman diagram, you replace each of the L0 inverses by these integrals of this kind. Okay. So there will be different T's for different propagators. Okay. And it's this integration over T's that become the moduli of Riemann surfaces after change of variables. Okay. So this is the way we make connection between the string field theory Feynman diagrams and the worldsheet moduli integrals. Okay? And in this language, the divergences that you see in the worldsheet, okay, all come from the t goes to infinity limit. Okay, that's the origin of divergences in the Riemann surface picture. Okay. So let's examine this formula in a little more detail. Right, L0 inverse is given by this. Now, if you look at this, you can see that this is an identity for L0 positive. Right? So the two sides are clearly the same. When L0 eigenvalue is positive, there is no question that this identity is a genuine identity. But when L0 is negative, the right hand side becomes divergent, right? Because the integrand is exponentially divergent. But the left hand side is finite. So remember, the left hand side is the string field theory expression. Right hand side is what is needed to make connection of the worldsheet. So what this is saying is that the worldsheet expression diverges from the t integral that is involved in the worldsheet expression diverges from the t equal to infinity end, but the string field theory expression remains perfectly finite because it's just 1 over a negative number. So if we use the string field theory expression, then there is no divergence that we'll encounter, at least from integrals of this kind. The more interesting case is the case of L0 equal to 0, because for L0 equal to 0, both sides are infinite. Okay, so now we cannot say that we will make sense of these divergences simply by using the left hand side, because the left hand side also diverges. Nevertheless, the divergence that appears on the left hand side has a meaning. Because this means, remember 1 over L0 is the propagator. Right? So divergence in 1 over L0 means that we are essentially sitting on a pole of a propagator. One of the internal propagators is going on shell. Okay. Now while this is bad, this is divergent expression. Okay. In quantum field theory, whenever an internal propagator goes on shell, right, typically it has a physical origin that we can understand by analyzing quantum field theory appropriately. And quantum field theory usually gives a remedy of what to do. Right? You never get stuck in quantum field theory with this problem of an internal line going on shell. Right? There are always ways to deal with those cases. Okay? And that is the same idea here, okay? That we'll use insights from quantum field theory to make sense of these divergences, the divergences that come from L0 equal to 0. Okay? Yes. Yes, yes. Yeah, you can just put I epsilon with a L0, right? L0 minus I epsilon. Yeah, this is the, okay. I mean, in string field theory, there is a specific way of introducing this I epsilon prescription, which is instead of using I epsilon, when you think in terms of momentum integrals, right? The momentum integral contours have to be tied to plus and minus I infinity at the two ends, right? Even when the external energies are Lorentzian. See, in normal quantum field theory, when you do weak rotation, right, where the I epsilon prescription comes from, is that you start by saying that the momentum integrals are along the imaginary axis, and then as the external energies are rotated to real values, the momentum integration contour also you rotate to the real values. Right? So in string theory, it turns out that that is something that is not allowed, because when you take the momentum integration along the real axis, the integral diverges. Okay? So what you do is that you keep the endpoints fixed at plus minus I infinity, okay? But in the middle, you deform the contour so as to avoid poles. So there's a well-defined procedure of how you do that in string field theory, right? And the same, so that's what you need to do. Yeah, I'll show you. I mean, for D-instantons, we'll see what the on-shell states are and how to deal with those. Unfortunately, the I epsilon is not going to resolve that problem, right? The on-shell states that we get on the D-instantons have to be dealt with differently. Some of the cases, as you said, are dealt with by I epsilon. Okay, so now let me start by discussing where the divergences are coming from. Okay, the specific case of diagrams in string field theory. Okay. So we are going to start from this annulus, because this is something that accompanies every Feynman diagram, as we discussed. Okay, we have written down the expression here. So what is this expression? So here T is an integral. Okay, so T is essentially proportional to the ratio of circumference to the width of the cylinder or the annulus, okay, whatever you want to call it. Okay, it's a ratio of this to this width. Okay. And Z of T is what is called the annulus, the open string partition function. Okay, so this is trace over open string states that live on the D-instanton, weighted by this particular factor. E to the minus T L0 is basically saying that the L0 is propagating the open string over a distance T. Okay. Minus 1 to the F takes value plus or 1 or minus 1, depending on whether you are summing over bosonic or fermionic states. And this B0, C0, these are the ghost zero modes. Okay, this is needed so as to remove the ghost zero modes from the trace. Otherwise, you'll just get 0 in this. In any case, you can just expand this out. Okay, and you can write this as sum over bosonic states, bosonic open string states on the D-instanton, weighted by e to the minus T times HB, where HB is the L0 eigenvalue of the bosonic state, and minus sum over the fermionic open string states, weighted by e to the minus T times HF, okay, where HF is the L0 eigenvalue of the fermionic open string states. Okay. And now from this formula we see that whenever HB or HF is negative or 0, then this integral diverges, right? When HB or HF is 0, for example, then this is logarithmically divergent integral. When one of them is negative, then it's exponentially divergent integral. Okay. So those are the sources of divergence in the standard worldsheet formalism. Okay. So here I have now given the strategy for dealing with these large sheet divergences. Okay. As I said, the strategy is always that you have to reinterpret this worldsheet contribution in terms of a string field theory contribution. Right? What is the corresponding field theoretic expression that produces this? Because once you understand that, then you can use the field theory insight to deal with these divergences. Okay. So the first, we use an identity which is, so these are the identities that are valid when these are positive, HB and HF are positive. So the first identity is just a mathematical statement. You can easily check that this integral is the square root of HF over HB. Okay. This just is a statement of a Gaussian integral. Right? I mean, all these normalizations are important because they are going to affect the final result. Okay. So this is the result of a Gaussian integral, and this one, this identity is just the rules of Grassmann integration. So PF and QF here are Grassmann odd variables, and psi b is a Grassmann even variable. Okay. So these first, these three lines are just standard identities. Then the next step is that we will interpret these integrals, okay, the integration over these modes, psi a, psi b, PF and QF, as integration over open string fields. Okay. Now when I say open string fields, okay, it's somewhat misleading because you are talking about open strings on D-instanton. Right? And on D-instanton, there is no space-time direction. D-instantons are localized in all non-compact directions. Right? So these are really discrete modes. Okay, so when you talk about fields, okay, in this case, these are just ordinary variables, 0 plus 0 dimensional fields. Okay, that's why you don't see any path integral, you just see ordinary integrals. Okay. So you interpret these as integration over the open string fields, and the exponents here are just the open string field theory action. Okay. But it's the open string field theory action in what we call the Siegel gauge. Okay, I should have said here that the Siegel gauge condition comes because this B0, C0, the fact that you have this insertion of B0, C0 means that this trace is taken over only on those open string states which are annihilated by B0. Right? And this is often called the Siegel gauge in string theory. Okay. So this is a formula that is valid for HB and HF positive, but now we are going to reinterpret, we are going to say that this is the expression that we are going to use, okay, when HB and HF are negative, because this is a string field theoretic expression. Right? This you think of as a fundamental object, and the worldsheet as something that you get from string field theory. Okay. So now in this language, you see, you can ask what happens, what are the interpretation of the modes with HB less than 0. Right? See, when HB is less than 0, this of course is divergent. Okay. But if you think of the psi b equal to 0 as the saddle point, okay, then this divergence simply means that the saddle point that you are talking about, okay, is not a minimum, okay, but is a real saddle, because in the psi b direction, it's a maximum rather than a minimum. The action has a maximum. Okay. And we know what we do in normal instanton physics, okay, that if you have a saddle point, okay, which is not a minimum, you integrate along the steepest descent contour. Okay, which means that in this case, you have to integrate psi b along the imaginary axis rather than the real axis. Okay. And that basically reproduces the same formula, okay, for a negative HB, right? So you'll get some extra factor of I, and that you can interpret as due to the fact that psi b integral is running along the imaginary axis. Okay. So for modes with HB less than 0, okay, we really don't have to do very much. Okay, we just continue to use this formula, okay, with negative HB. So even though this is not well defined, right? This is divergent integral. Okay. Again, as before, the modes with HB equal to 0 and HF equal to 0 are the subtle ones. Okay. These represent bosonic and fermionic 0 modes, and these have to be treated carefully, right? And I'll now describe how these are treated. Okay, what to do with the modes with HB and HF 0. So to deal with this, you have to understand the origin of the 0 modes, right? Where are these 0 modes coming from? What is the physical origin, right? Because that's what you do in quantum field theory. Whenever you have a on-shell propagator, okay, or whenever you have a massless mode, okay, we have to understand what is the origin of that massless mode and then find a resolution. Okay. So the 0 modes come from various sources. One class of bosonic 0 modes arise just from the freedom of translating the instanton along flat directions, like the Euclidean time, right? I said the instanton is localized in the Euclidean time, right? It's Dirichlet boundary condition also along the Euclidean time direction, but this means that you can place the instanton here or here or here, anywhere in the Euclidean time direction. Similarly, along the flat spatial directions. Okay. So this ability to move the instanton along those transverse directions is a 0 modes. Okay. And those will appear as psi b with 0 HB. Okay, those will definitely give rise to 0 modes on the instanton. Okay. And the remedy that one has to follow is the same as what you do in a normal quantum field theory. Okay. That when you have instantons which are localized in space and time, we treat the position of the instanton, okay, in the space-time coordinate as a collective mode. Okay. We don't try to treat those degrees of freedom using Feynman diagrams. Okay. Instead, we keep them frozen till the very end, and we do the integration over those modes at the very end. Okay. And exactly the same thing we have to do here. So the strategy here will be that you have to change variables from the bosonic 0 modes to the D-instanton position y. Okay, the 0 mode variables, the psi b's that we introduced, okay, the psi b's correspond to the 0 modes. They are not exactly the instanton position, okay, but there is some Jacobian. Okay, typically there is a relation between these 0 modes and y, and you have to change variables and you have to carefully calculate and pick up the Jacobian factor in the path integral. Okay. After you have done that, you keep the variables y frozen till the very end. Okay, at the end you have to integrate over y. And a similar treatment is needed for the fermionic 0 modes associated with broken supersymmetry. And now I should just note here that the fact that you have to integrate over the 0 modes, over the collective coordinates of the instanton, right? Normally one thinks that whenever you are talking about D-instantons, right? D-instantons have a given position. Are you supposed to integrate over those positions? Okay. And the answer is that you don't do it unless string theory tells you to do it. Okay. So you keep those positions fixed, right? See what string theory is telling you. And in the string theory path expression, you will already see that there are these 0 mode integrals. Okay. And that is what tells you eventually that you have to integrate over those 0 modes. Right? So the lesson is that you don't do anything unless string theory tells you to do it. Okay. And string theory knows what to do. Okay. And it does tell you that you have to eventually integrate over these positions. Okay. Now the second set of 0 modes, and these are fermionic 0 modes coming from the ghost sector. Okay, these are unusual ones. These are not what you are normally familiar with in quantum field theory, but I'll explain where they are coming from in the language of quantum field theory. Okay. So these are arising from the ghost sector. Okay, the vacuum has L0 equal to 0. Right? And similarly, this C1, C minus 1 on the vacuum, this also has L0 equal to 0. So these are a pair of L0 equal to 0 states. Okay? They satisfy Siegel gauge condition because B0 acting on these states give you 0. So these are fermionic zero modes. Okay? And so you have to learn how to integrate over this. What is the origin of these fermionic zero modes and how to deal with them. And what I'll show you now is that these arise because they are the results of wrongly fixing a U1 gauge symmetry on the instanton. Okay, and I'll explain what we mean by wrongly fixing the U1 gauge symmetry on the instanton. So for this, let's consider the gauge invariant open string field theory on a D brane. Okay, not necessarily D-instanton, just an arbitrary D brane. Okay, D plus one dimensional D brane. So this, as you know, has a U1 gauge field. At the quadratic order, its action is just a Maxwell action. But when you actually start from string field theory and calculate the quadratic part of the action, we find that the quadratic part of the action is not just the Maxwell action. There is an extra term, okay, which is here. This phi is a scalar. What is a scalar? So in the language of string field theory, okay, this is the scalar that multiplies this state over here. Okay, for every mode you introduce a field, right? So this is a particular mode of the string. So for this you introduce a field. What is peculiar about this scalar, okay, is that this doesn't satisfy the Siegel gauge condition, right? So this is out of Siegel gauge. B0 acting on this doesn't give you 0 because B0 C0 has a non-zero anti-commutator. So this scalar field is not present in the Siegel gauge, okay, but this is a gauge invariant form of the action. Okay, we'll see how to get the Siegel gauge from here. Now this part of course is manifestly gauge invariant, and indeed this is also gauge invariant because we can write down a gauge transformation law of this form. Okay, you can see that these two terms cancel. Okay. And this in fact is nothing but the Maxwell action because phi is an auxiliary field, right? Phi has no kinetic term. So you can just integrate out phi and get rid of this. Okay. But string field theory gives this phi. Okay, so let's keep this phi for now. So here I have written down the action and the gauge transformation laws. Okay. Now let's see how we recovered the standard worldsheet formalism, worldsheet picture. Okay. And for that you go to Siegel gauge, right? We fix the gauge phi equal to 0, okay, which is possible because phi varies under gauge transformation. Okay. So when you set phi equal to 0, okay, you set phi equal to 0 here. These two terms combine to give you the standard Feynman gauge action, which is here. Okay. But because the phi has a Laplacian acting on theta in its gauge transformation law, when you set phi equal to 0, there is a Jacobian, okay, the determinant of the Laplacian that you have to pick up, and that essentially gives rise to the Fourier-Popov of ghosts, right? The integration, the path integral over P and Q basically produces the determinant of the Laplacian. Okay, so this is Fourier-Popov of ghost. Okay, and that's what you get in normal gauge fixing in a general D brane. But now let's see what happens when you focus on D-instantons. Okay. D-instantons are zero-dimensional objects in space-time. So there is no mu. And there is no space-time, right? So obviously all fields are x-dependent. There is no x. There is no world volume of the D-instanton. Okay. So this is identically 0. Because there is a box, there is a box. This is identically 0. Okay. And this is the origin of the ghost zero modes. Right? You saw these two ghost zero modes, P and Q, right, corresponding to the vacuum and the C1, C minus 1 vacuum. These are the origin of the ghost zero modes for the D-instanton. Okay. And one can also understand why it's arising. Right? Because you see, on a general D brane, right, this is a perfectly valid gauge fixing procedure. But on a D-instanton, phi doesn't transform under a gauge transformation, right? Because the box is just 0. Okay. So you are trying to gauge fix a field phi, okay, which doesn't have a gauge transformation law. So clearly you are going to run into a problem. Okay. So the fact that you are getting the ghost zero modes, okay, is a result of attempting to gauge fix something that you are not supposed to gauge fix. Okay. worldsheet tries to do this gauge fixing, right? Because the worldsheet essentially treats all the D branes on the same footing. It doesn't know that it has to give special treatment to D-1 brane, right? The D-instanton. It just treats the D-instanton in the same way as a DP brane. Okay? And in that process, it makes this mistake and introduces these ghost zero modes. But once you have understood what is the origin of this problem, okay, we also can find the solution. So what is the solution? So the solution that we will take is that we basically undo the gauge fixing, right? We don't have to gauge fix. Okay. So use a gauge invariant form of the path integral, okay, which means that you don't gauge fix phi, we actually integrate over phi and drop the integration over the ghosts. The ghosts came from the gauge fixing. Yes. See, the U1 gauge field really has no analog in the bulk, right? So I'm not sure that there's a bulk understanding of this, of the origin of this field. At least I'm not aware of any bulk understanding, right? It seems to be specific to the world volume of the D-instanton. Okay. So ungauge fixing means you have to integrate over phi, right? You are not supposed to gauge fix phi. And we don't introduce a ghost, so we drop the integration over the ghosts. And then you have to separately divide by the volume of the gauge group that is given by the period of theta. Okay. And this has to be found by carefully finding the relation between theta. See, theta is a string field theory gauge transformation parameter, and the standard gauge transformation parameter is this alpha, right, where the state transforms to the phase a to the I alpha. In terms of alpha, of course, you know that the volume is 2 pi, right? Alpha has period 2 pi. So once you find the relation between theta and alpha by carefully comparing the string field theory gauge transformation laws with this gauge transformation law, we can find out the volume of the gauge group in terms of theta. Okay. So this is now a well laid out procedure that we can follow to find out what this object is. Okay, and I'll give an example of this in a few minutes. Well, here it is. Two-dimensional string theory. Okay, so two-dimensional string theory, the worldsheet. Okay, I think you don't really need the worldsheet. Okay, let's forget about it. So it basically has two scalars. One is a time direction scalar and one is the space direction scalar. Okay, but the space direction is an interacting scalar field, right? The Liouville is central charge 25. But the main point is that it has a D-instanton, okay, and its annulus partition function is given by this. So first, you see that this is divergent, clearly. As from t goes to infinity, this diverges. This also diverges logarithmically. So e to the t is easy to handle because you have understood that e to the t is a result of tachyon. This means that there is a state with L0 equal to -1, right? HB equal to -1. So you get a square root of 1 over square root of HB, right? Which you replace by I. Okay, so this will give I. So the most divergent part, in fact, is easier to handle, right? It's the logarithmic divergent part that is that requires more care. So this -1 that you see means that net number of zero modes is -1, but this is the result of 1 bosonic zero mode and 2 fermionic zero modes. The bosonic zero mode essentially is associated with the translation along the x direction, along the time direction. And the fermionic zero modes are coming from the ghosts that we described, the vacuum and the C1, C minus 1 on the vacuum. So the contribution from translation zero modes, we have to find a relationship, as I said, between the psi b and the actual position of the instanton along the time direction, which I am calling y here. And this relation one can find by some calculating string amplitudes. And one finds that a precise relation between the psi b and y has this extra normalization factor, where this GO is related to the string coupling by this factor. Okay, this just is a pure worldsheet calculation. Okay, you have to do this calculation, but you can figure out the relation between these two. After you have done that, the integral dy, okay, this integral has to be done at the end. Remember that the y integral is the integration of the d-instanton position. This integral at the end will basically produce this energy conserving delta function. Okay. So even though the individual world sheets don't have energy conservation, okay, at the end, after you integrate over the zero mode, over the position of the D-instanton, you will get the energy momentum conservation. And then the ghost zero mode integral, okay, we are supposed to drop this, and you have to integrate over this variable phi, right, which cannot be gauge fixed, okay, and divide by the volume of the gauge group. Okay. So this integral, the numerator gives you as root pi, and the volume of the gauge group after finding out the relation between theta and that standard gauge transformation parameter alpha, you get this factor of 2 pi over GO. So by putting these together, putting this, and then this, and that factor of I that we got in the previous slide, here, okay, this I over here, the final answer that we have is this, I over 4 pi square. And this agrees with the dual matrix model result. Okay, this was one of the checks that this procedure is really giving you the right result. Okay, because here, unfortunately, we knew what the results would be. Okay, so this in fact can be continued also at higher order. And I'll write down some Feynman diagrams. Okay, so the disk 2-point function has divergence from the region where one vertex operator approaches the boundary. This I have already said. The annulus 1-point function has divergence from the region where the vertex operator approaches the boundary, or the parameter t that measures the circumference to the width ratio becomes large. And all these divergences can be associated with the zero modes or tachyon in the propagator. Okay, so the idea is that you represent these amplitudes as Feynman diagrams, and then all divergences are basically the zero modes in the propagator. Okay, so let me give you some example of Feynman diagrams. Okay, maybe I should say the strategy. Okay, this I've already said, but I'm repeating it. Okay, so the strategy is that we express the amplitudes as sum over string field theory Feynman diagrams. Okay, once you do that, it automatically replaces the tachyon contribution by 1 over h, where h is the L0 eigenvalue. Right, so tachyon contribution is already taken care of once you use the string field theory Feynman diagrams. But the zero mode contribution are not taken care of just by this step, by step 1, because Feynman diagrams you still treat propagator as 1 over L0, right? So L0 equal to 0 state, so it will give you 1 over 0. What you are supposed to do is to remove the zero mode contribution explicitly, because we are not supposed to integrate over the zero modes, right? They are to be integrated at the very end. They are not to be treated as by Feynman diagram method. So you explicitly by hand remove the contribution to the propagators from the zero modes, and also we have to add the propagator of the field phi, because this was not present in the world sheet formulation, but it should be present, because phi was gauge fixed, but that gauge fixing was not allowed. Okay, so you are supposed to explicitly integrate over phi, which means in the Feynman diagram language, we should include the phi propagator in every open string internal propagator. So here I have given the diagrams. Okay, so this is the contribution from the disk 2-point function of two closed strings. So the convention here is the thick lines are the external closed strings and the thin lines are the open strings, and these crosses are thus the interaction vortices. Okay. So you see here this diagram can get divergence when the internal open string has a zero mode. Okay, we have a 1 over L0. Here again the internal open strings can have 1 over L0. So those are divergences, and the procedure is that you basically remove those 1 over L0 pieces by hand. Okay. And then instead you put in the phi propagator. Right? You have to sum over all possible insertions of phi propagators in the internal line. So let me again give some example of what kind of result it gives. Okay. So here again we have results in two-dimensional bosonic string theory. Okay. So instead of dealing with the disk 2-point function directly, I have defined this f, which is essentially the ratio of the disk 2-point function and product of two disk 1-point functions. And omega 1 and omega 2 are the energies of the external closed strings. And similarly, this ratio G is the ratio of the annulus 1-point function to the disk 1-point function. So when one computes this in the world sheet, okay, forgetting about string field theory, one gets a integral of this kind, right? So f has a finite piece, okay, which can be evaluated numerically, okay, plus something which looks divergent, right? This integral diverges as y goes to 0. Y here is roughly the distance of one of the vertex operators from the boundary. Right? So the y goes to 0 divergence is a divergence that is coming when the vortex operator approaches the boundary. Okay. G again has a finite piece, and then it has double integral. Okay. One of the integral is basically the ratio of the circumference to the width of the annulus, and the other variable is the distance of the vortex operator from the boundary. Okay. And again, you see that this has divergences from the x equal to 0 n and the v equal to 0 n. So you take these expressions and then run it through the machinery of string field theory, right, and see what we get. Okay. So I'll only give the final result because it's a straightforward but tedious procedure. Okay. So at the finally, okay, after processing it to string field theory, you get a perfectly finite answer of this kind. Okay. So this is the same finite pieces, and then the divergent pieces are replaced by these quantities over here. Here lambda is an arbitrary constant parameter that labels string field theory. Now this seems a little strange, right? The final result shouldn't depend on some arbitrary constant parameter. You are supposed to get an unambiguous answer. Okay. And the reason that lambda appears, right? I mean, why are there more than one string field theory, right? What this is saying is that there is a family of string field theories labeled by lambda. Okay. But what one can show is that that family of string field theories are all related to each other by field redefinition. Okay. So the physical result shouldn't depend on lambda, right? Intermediate steps can depend on lambda. Okay. So now let's see if the physical results actually depend on lambda or not. Okay. So here I have given, okay, these are the expressions for f and g again. Okay. But when you use this to compute an amplitude, right? Remember an amplitude contains both this 2-point function and annulus 1-point function. They appear in the same order, right? So if you take an n-point amplitude and you see what combination of f and g appear in the expression for the n-point amplitude, okay, one finds that the particular combination that you have to deal with is this one. Okay, the sum over I less than j f omega I omega j and sum over I g omega I. Right? This basically means that when you're considering an ordered GS suppressed contribution, you can put any 2 pairs of external closed strings on a single disk. Okay, or you can take any of the external closed strings and put it on an annulus instead of a disk. Right? That's the sum. Okay. And you can easily convince yourself that once you impose a total energy momentum conservation, right, sum over omega I equal to 0, okay, the lambda dependence just drops out. Okay, so this is completely well defined, unambiguous, has no dependence on lambda. Okay, even though these intermediate objects f and g do depend on lambda. Okay. So this is basically saying that indeed the lambda of course will appear in the intermediate stage of the calculation. Okay, anything that is not on shell will be affected by lambda, because different string field theories are related by field redefinition, and off-shell quantities do depend on change by field redefinition. But all on-shell amplitudes are unaffected by field redefinition. So using this, we can get a completely unambiguous answer for the amplitude, the GS suppressed contribution to the amplitude. Okay. So this has been tested in many examples. Okay. And when the result is known from a dual description, this procedure produces the correct result in all cases that have been studied. Okay. In fact, there are some issues earlier where some things are not matching, but now, okay, every case that has been studied and that can be matched compared to the dual result, the results agree. Okay. And here are various examples where it has been studied. C equal to this is 2-dimensional bosonic string theory, minimal bosonic string theory, and then more standard critical superstring theories, okay, both in D equal to 10 and also in Calabi-Yau compactification. Okay. And finally, this has also been applied to compute D-instanton correction to the superpotential for n equal to 1 supersymmetric compactifications of string theories, okay, where the answer is not known. Okay, but we use the same method, and presumably, since it works in all other cases, the answer is correct, whatever you get from this particular procedure using string field theory. Okay, so I think my time is up, so I'll just conclude. Okay, maybe I'll just skip this. I'll go to the conclusion. Okay. So the conclusion is essentially that the worldsheet theory, with the help of string field theory, provides a fully systematic procedure for computing D-instanton contribution to an amplitude. Okay, and in principle, if you want to know the answer to any D-instanton induced process, you can use this strategy to find the result. Okay, the non-perturbative contribution to string amplitudes. Thank you.
So much, Ashok. Questions for Ashok? Further questions? Of course.
Hello. Yeah, thanks for the nice talk. So one can see that this is very sophisticated computations. Could you go back to your motivation at the beginning where you listed possible insights one gains from having computed the instant contributions, and maybe say us what we learn now from the computation? Does it illuminate duality? So you mentioned the check to the matrix model, which I think serves to show that things are consistent, but it also seems to reproduce something we already knew, right?
Yes, indeed.
Could you maybe highlight what apart from the concrete computation, what a general insight on string theory might be that is gained from this computation?
Yeah, see, the point is the calculation of the superpotential induced by D-instantons is an important problem in string theory because those are used in moduli stabilization. When you look for the vacuum where all the moduli are stabilized, right, you need to use non-perturbative superpotential. And those are generated by D-instantons. And to find the minimum, to see whether their minimum exists or not, you have to calculate the D-instanton contribution to potential. And that can be done using this method now.
Has it been done, or is this something?
Yeah. This is one of the things I mentioned, that we didn't do the moduli stabilization, but we gave the general formula for the D-instanton induced superpotential.
I see.
In this list, this was last in the list.
I see. Thanks.
Work here. We use this method to compute D-instanton correction to the superpotential. And here the point is that the perturbative contribution vanishes. So D-instantons are the dominant contribution, which you have to use to stabilize the moduli.
I see. Thanks.
Any other questions? Sasha?
Thank you. In the beginning of your talk, you mentioned that your approach to computing D-instantons can resolve divergences in computing integrals over the modular spaces of Riemann surfaces.
Yes.
What modular space are you talking about? Is it infinite dimensional or finite dimensional?
No, this is finite dimensional because because these are just moduli spaces of Riemann surfaces.
And the divergences are due to the fact that the integrals don't extend to the compactification of the
exactly.
modular space?
Yeah. The integrals basically diverge at the compactification.
I see.
Yeah. These particular examples that I gave, let me show the expressions. Yeah, here, for example, this is this two-point function, right? And y is the boundary where one closed string is approaching the boundary. Y equal to 0, right? Is when closed string is approaching the boundary. In terms of degeneration, it's like two disk one-point function joined by a strip, and the strip is becoming long.
Yeah.
And that has a divergence, right? So the integral you cannot do the integral directly there.
Okay. Thank you very much. Yeah.
Okay, great. Any other questions? Chris?
Thank you. It's very interesting the way the string field theory gives a very good picture of what's going on in a way that the world sheet theory doesn't. Is there a way of thinking about what you now understand from the string field theory in world sheet terms, or are you forced to look at from the string field theory point of view?
Yeah, of course, this I have been thinking about it. I think several people have been asking and thinking about it, but so far there doesn't seem to be a good world sheet picture. Right? Of course, all the techniques that we use are world sheet because string interaction vortices are computed using world sheet techniques. But the final formula that you have to replace the open string the massless propagators and replace it by the phi propagator, whether that has a direct world sheet interpretation, right, is not clear. Even though the individual pieces are computed using world sheet description, right? If you want to calculate, for example, a phi propagator connecting two disks, the vortices as well as the phi propagator is computed from the worldsheet correlators. Right? But the whole thing doesn't have a direct worldsheet picture, at least as of now.
Thank you.
Yes.
Coming back to the question that was asked, if you manage to compute the non-perturbative correction coming from the instantons, and therefore find that the vacuum of the theory should not be flat space, but something else like de Sitter, doesn't this invalidate the use of perturbative techniques?
Yeah, okay. I mean, it's probably, it's true that in some cases, if you find that the place where the moduli are stabilized is very far from being flat, that of course will invalidate the perturbative techniques, because then that means that if the coupling constant, for example, is of order 1, then you don't have perturbative control. But what people do in this kind of KKLT compactification or flux compactification is that you don't have a continuous parameter because it's get fixed. The coupling constant will have to get fixed. But you can use ratios of fluxes, okay, which are integers. Okay. Nevertheless, the ratios of fluxes can be adjusted so as to make this coupling, the minimum where the place where the potential is minimized, occur at weak coupling. Okay. You cannot make it arbitrarily weak, but you can, for example, you can, if you take the ratio to be 10, okay, ratio of fluxes, you can make the coupling constant of order 1 over 10. So you don't have a full perturbative control. Okay. And that, I mean, in real world, you don't expect, because standard model coupling constant is not 0, right? It's some finite result, finite value. We do perturbation expansion in the standard model coupling constant, but it's not clear that there is a full UV complete theory for arbitrary value of the standard model coupling constant, which also includes gravity. So what you are saying is true, that you don't have a full control, right? But you don't expect a full control in the real world, right? And but the best one is to hope for is that if we can stabilize the coupling constant at some value like 1 over 10, that may be good enough for the kind of accuracy that you want.
Thank you.
So the D-instantons, you can think of it as additional saddles that you want to consider in the string amplitude.
Yes, that's right.
From this point of view, how should I think about this phi field, which is stuck on the D-instanton?
Phi field, okay, it's not one of the asymptotic states of the string theory. It's the mode of the D-instanton. Right? So D-instanton is a saddle, and the phi field is some kind of collective motion of the saddle.
It's a collective mode that lives on the saddle itself.
Exactly, that's right. So all the open string modes are the collective modes that live on the saddle, so which have to be integrated out at the end.
Okay, thank you.
Yeah.
Let's see, any further questions? Okay, if not, let's thank Ashoke again for the very nice talk.